Alright, this is Unit 7, Lesson 1 of our Calculus class. Unit 7 is Applications of Integration. Lesson 1 is Area between two curves. So we're going to talk about how to use integral calculus to find the area between two curves, two smooth curves, and how to write that calculation. So consider f of x and g of x intersect at points A and B, and they overlap in between. And so if we want to find the area between these two curves, what we can do is we can find the area underneath the curve of g of x, because that's the top function is g of x. So the area under the curve of g of x from A to B, and then we subtract the area under the curve of f of x from A to B. So g of x minus f of x gives us this area in between the two curves. Our calculus notation would look like this. The integral from A to B of g of x, the top function, minus f of x, the bottom function, would be equal to the area under the curve of g of x subtracting the area under the curve of f of x, both on the intervals of A to B. So that's kind of our setup, our game plan for finding the area between two curves. We need to know which function is on top, which function is on bottom over a given interval, and we need to know the starting point and the end point interval. I'll say that twice now. Okay, so what about if it's underneath the x-axis? Because if you recall from our Unit 6, if there's an area underneath the x-axis, it's actually a negative area. But when we do the subtraction, you'll find that the negative kind of washes out, and it gives you a positive area value regardless. So consider this f of x and g of x on the interval of A to B. If I say the area under the curve, f of x would be the top function from A to B, and g of x would be the bottom function from A to B. And so if I consider that region R, I can find the area underneath the curve of f of x, which would actually give me the area above the curve, between the curve and the x-axis. And g of x would give me the same, above the curve all the way up to the x-axis. And those integrals would each be a negative number because, like I said, they're below the x-axis. However, if I take the area under the curve of f of x is smaller than the area under the curve of g of x. And so since g of x is a bigger negative, it will be less than f of x, but its absolute value would be greater than f of x. In other words, this area is bigger than this area. So if I take this area and I subtract a bigger area, and both of those areas are negative, I'm subtracting a bigger negative, which means I'm adding a bigger positive than my original negative is. And that's a lot of confusing negatives and positives. So I'll say it one more time. This is a small negative, this is a bigger negative. So a small negative minus a bigger negative means I'm taking a negative and I'm adding a number that's bigger in magnitude or a bigger absolute value. And so if I do that, I'm going to find that we're actually going to get a positive result. That's going to work every time. So now that we're looking at area between two curves, the bottom point is I don't have to worry about positive or negative as it pertains to above or below the x-axis. That kind of takes care of itself. All we have to do is find the integral from A to B of the top curve minus the bottom curve, dx. Let's look at some examples. So I want to integrate to find the area shaded in green. So my a value, my starting intersection point, is when x equals -1. My b value, my ending intersection point, is when x equals 0. So we're going to integrate from -1 to 0. If I'm looking at these functions, I know that g of x is the top function because they're both parabolas, they're both x squared functions, but g of x is a negative leading coefficient, so that means it's going to be a concave down, it's going to open down, and so that's how I know this is g of x. And then by the same logic, positive 3x squared for f of x is going to give us a parabola that opens up. So when I set up this integral, I'm going to do the top curve minus the bottom curve. So g of x minus f of x dx. So here's our setup for finding the area between the curves. I'm going to substitute in negative x squared x squared minus 2x for g of x. I'm going to substitute in 3x squared plus 2x for f of x. And I'm going to perform the subtraction and simplify our polynomial. I'm going to integrate on the interval of negative 1 to 0. So I'll do those calculations, plug in 0, and then plug in negative 1 and find the difference. We end up with an area of 2/3. And we're not really given a unit of measure, so we can't put a unit of measure. Another example, the area between these two curves. The a value, the starting point of our interval, is when x equals negative 1. The b value, the end point of our interval, is when x equals 2. F of x is the top function and g of x is the bottom function. So our region is found by integrating on the interval of negative 1 to 2 of f of x, the top function, minus g of x, the bottom function, with respect to x. Substitute in for f of x and g of x, the polynomials. Simplify, integrate on our interval, and we get the answer as 9. Okay, so that's it for this lesson. We can use integral calculus to find the area between two curves. And yeah, I think Willie says it all right there. So that's that.